Welcome to the Navigating Nuclear Science Creating Teacher Workshops. My name is Linda Zek, and I am the Online Communications Specialist here at ANS. On the line right now, we have Janice Lindegard, who is the ANS Education Specialist, Candace Davison from Penn State University, Mary Lou Dunzik-Gougar from Idaho State University, Eric Loewen from GE Hitachi Nuclear Energy, and also a past ANS president, and Bill Wabbersen, ANS Savannah River Section. I'm going on mute at this point. Janice, you can take over.
Thank you. Hello, everyone. Linda's already gone through who will be presenting. Today, we are going to be talking about why it's valuable to do workshops. We're going to introduce the new workshop presentations that we've developed, and we'll be talking about the support that ANS has available for members and non-members. And now I'll have Eric talk about the value of teacher workshops. Eric Loewen is an ANS past president and the chief engineer at GE Hitachi Nuclear Energy.
Thank you, Janice. So the picture you have before you is one of the many teachers workshops that I've had the opportunity to be a part of, and you see teachers in the room holding some very old Geiger counters. So the value of teacher workshops is what I'll introduce with, and then we can move on to the other subjects. So the next slide is titled Why Workshops. The idea is to get some ANS members of a diverse background, and that's your panel that you have today, to provide the teachers with content knowledge that they may have missed as they're going through college or through their science program to be able to use in the classroom, to counter some of the myths and misconceptions with nuclear science and technology that we are aware of. And then we actually want to give these teachers some tools and strategies for their students in the classroom. And in the picture that you saw before, we actually give them some Geiger counters. And in the end, we want to put a human face on our industry so that they can see the value of teaching in the classroom and that there's career opportunities for the students that they're teaching. So a little bit about the history on the next slide. We started these national workshops about 1999 because as a society, we have two national meetings in different parts of the United States. And the thought was that the leaders at the time is we have all this talent coming to these different cities. What if we showed up a day early, invited teachers in the local area to attend a workshop, we'll feed them lunch and we'll give them a whole bunch of tools, and that's how it initially got started. The Department of Energy provided some funding in the early 2000s. That allowed us as an organization to provide more tools to the teachers because it deferred some of our costs because we're volunteers, so it didn't cost there, but we were able to give more things to the classroom. And when DOE funding, because of different policy changes, stopped, we were still able as a society to continue it forward. So it's been a long history. And then the beautiful thing about it is we have a lot of local sections within the American Nuclear Society that saw the value of a workshop, and they were able to use the information or go on their own to do workshops in their local area, just as Bill does down at Savannah River. And by our count, we feel that we've reached about 17,000 students.
That's a very conservative estimate based on just 2 workshops a year, 25 teachers each, and an average of 35 students per teacher for 20 years. I'm sure we've reached far more students than that. The impetus behind revising the American Nuclear Society approach to teacher workshops was the advent of the next generation science standards. The standards now include nuclear processes as part of the disciplinary ideas that students should know. This includes fission, fusion, radioactive decay, particularly alpha, beta, and gamma, half-life, and the release of energy. Now, this wouldn't be such an issue except that now nuclear processes are also part of standardized testing. So any of the 19 plus 21 states who are based on either the NGSS or on standards that are based on the NGSS will be assessing their students on their knowledge of nuclear process. So what we've done is we have revised what we teach in our workshop content, not changing the content too significantly, but aligning what we're teaching to the next generation science standard. We've also incorporated some of the Navigating Nuclear lessons that we have. Navigating Nuclear is a K-12 education initiative that the American Nuclear Society developed with Discovery Education. There are lessons on nuclear energy and also a lesson on measuring radiation, and those lessons are aligned to the NGSS. We then created our workshop content into a modular format, and what that means is each of the presentations can be mixed and matched. You can use one module to teach just radioactive decay to teachers, or you can combine however you see fit in order to do a half-day workshop or a full-day workshop. And now I will pass it over to Mary Lou Dunzik-Gougar. She is the Associate Dean in the College of Science and Engineering, Associate Professor of Nuclear Engineering at Idaho State University. And Mary Lou will give a brief description of our radiation basics and radioactive decay module.
Okay, hi everybody. I am a professor at Idaho State University, so I teach nuclear things, but in a previous life I was a high school teacher. And so I have a real feeling for the nature of the material that is and isn't available to a high school teacher and how it's kind of hard to be a specialist in anything. So I have found great reward over the years, great gratification in doing the workshops because it's a really valuable thing for teachers. So if any of you out there are considering a teacher workshop, I highly encourage it. And again, I think that number of students that was mentioned on the slide is probably very low compared to the careers of all the teachers I've worked with. Traditionally, I will give a presentation at our ANS workshops on radiation basics and decay, sort of right at the beginning of the workshop, because I have found that all questions, concerns that people tend to have about things nuclear kind of boils down to maybe not completely understanding or having all of the information they need about the nature of radiation. And that can be applied to waste, it can be applied to power, it can be applied to nuclear medicine. We talk about decay in the most common types that are in our naturally occurring materials, so alpha, beta, and gamma decay, the half-life aspect of decay, and the fact that what's released from that process is the radiation that is the radiation specific to nuclear processes, pretty high energy. So as part of the standards, students are required to be able to develop models of nuclear processes. Okay, so one of those nuclear processes could be radioactive decay. And the standards specifically state that students need to be able to distinguish between alpha, beta, and gamma radiation. And I think it's really important in the workshops for the teachers to counter the idea that, you know, gamma radiation creates superheroes like the Hulk and Spider-Man. And of course the teachers don't believe that, but it's nice to give them a little background. And also just necessary to understand the other forms of radiation, what they are, what they aren't, how they may be used in various applications. So the focus on the module is how decay happens, distinction among the types of decay, emphasis that decay is a naturally occurring phenomenon. So it is a nuclear reaction, but it's a naturally occurring nuclear reaction that happens all the time, around us, in us, part of our world. Teachers can use these, obviously, these phenomena where things happen naturally, and radiation is also applied as ways to introduce the topic. So the fact that we are radioactive, the fact that all of our space probes that have gone any distance into our solar system has been powered by radioactive decay. The fact that we can date things that are very, very old according to the decay of certain isotopes in those materials. We want to give them tools other than the kind of fallback of nuclear weapons. I've seen it time and again that that's sort of the default. And it's just mostly because there's not a lot of awareness of all the different ways that radiation is used in our world. So some of the things we do in the workshops are provide them with ways to demonstrate concepts, especially abstract concepts. And decay is, because you can't see it, a little bit abstract. We use things like, I'm sure you've all heard of using M&Ms to model half-life, where you have a bag of M&Ms and you shake them around and dump them on your table. And the ones that have the M up or the W up or the E up, whichever it reads to you at the time, that's still radioactive. And the ones that have that letter down have decayed. And you repeat that process and you get a nice exponential decay plot from the number of M&Ms that are left over. You can do this sort of exercise, and these activities are all spelled out as part of the Navigating Nuclear Materials. But you can use anything that's basically double-sided, okay? You can use coins or puzzle pieces to do that. That activity in particular is especially good if you're talking about maybe a high school class where you can have graphing as well, and data analysis, and talk about, well, if you only have 10 M&Ms versus 100 M&Ms, you get better statistics, and the combined exponential decay curve really looks like a nice smooth curve. You can go pretty far with that depending on the level of your students. We use licorice, believe it or not, to illustrate that atoms have different half-lives, or nuclides have different half-lives, but the decay is still exponential. So again, this activity is described, but the basic idea is you take a red Twizzler and a brown Twizzler, and you plot one Twizzler at the beginning of your 0 time scale, and you mark the full height of that. And then you cut that in half and move it over next on the paper on the plot, and you mark the half height. And you keep going and cutting it in half, and then your marks on the paper look like an exponential curve. Then we take another isotope of Twizzlerium, and we start at the beginning, time 0, with the same height on the paper, but we change the time at which you break the Twizzler in half. And so that as you go across graph paper and you're putting the height of your licorice, that the exponential decay curve has a different slope. So it illustrates they're both exponential, but it demonstrates that they have different half-lives, so that the curve has a different slope. There are other activities we use to show the different isotopes, to show how when things decay, it changes the composition of the nucleus and what things come out. One method we use is something that I've yet to master after all these years, but I admire those who can do it, using balloons. So for example, you can have 2 white balloons and 2 colored balloons, and you kind of put them, tie them together at their ends, and that's an alpha particle. You compare that to, let's say, something that's the size of a pea, which would be like a beta particle. And you can throw them both, from your hand across the room and demonstrate, okay, the alpha is big, it's charged, it doesn't go very far until it loses energy. Meanwhile, the beta, much smaller, less charged, will go much further. You can also demonstrate, and this is the part that I haven't mastered yet, the neutron decay that effectively produces a beta particle. So demonstrating how a neutron basically turns into a proton and releases a beta particle. And this is where you blow up a balloon in a balloon, and between the two you have the little pea-sized thing, and when you poke the outer balloon, which is effectively the neutron, the beta particle pops out, and what's left is the proton. It's a delicate procedure. All right, so those are just some examples. Another really interesting tool we've been using in recent years is an isotope discovery kit that I just recently used in one of my undergraduate classes here at the university, and I can't say how much fun it is. And with that, I'll turn it over to Bill Wabbersen, because he is the isotope discovery kit guy.
This is Bill Wabbersen. I'm a nuclear engineer. I work at the Savannah River site in Aiken, South Carolina, and I've been doing nuclear outreach since about 1989, so I've been doing it a long time. But it really kicked off heavily for us in the central Savannah River area, which is near Augusta, Georgia. since the 1950s, the nuclear industry has been the major industry in that region. We have the Savannah River site with a lot of employees. We have Plant Vogel across the river with 2 existing plants and 2 under construction that are nearly completion. So we've always had a nuclear-friendly culture in our region. But in 2009, we started looking at how some local organizations with the American Nuclear Society started looking at how do we have the students to replace workers that are retiring, and do we have enough for the growth that we're having? And so we did it. There was a study done in 2009 by a local organization, and they found out we needed 10,000 nuclear workers in 10 years. So it was kind of we had our own little minor crisis. How are you going to train the local students to really understand the nuclear industry? So we got this group together to create local teacher workshops, and we used a lot of what the American Nuclear Society teacher workshops were doing. We were going to create teacher workshops, but we had 2 principles we had to have. We said we have to have hands-on presentations in every presentation. There has to be hands-on activity. So it was actually, how do you do that with nuclear technology? It's pretty difficult, but you've heard some of Mary Lou talking about some of the things we had discovered. But we had created a display that was in a local museum, and we watched people struggle with it. They could not understand. So one of the principles is trying to take someone from where they know to a new place. And so we focused on the periodic table because students and teachers know the periodic table. So we took that periodic table and then used the idea of what is an isotope. And if you visualize the periodic table, the isotopes, if each of those squares was a tile, like a Scrabble tile, and if you stack the isotopes up, you end up with all of the isotopes. So it's really the focus on the idea of an isotope. And so we took that and we started converting that to a chart of the nuclides, which is a horizontal chart. It's the y-axis is the number of protons, which is equivalent to the element title, and the x-axis is the number of neutrons. And so you can take that 3D periodic table and present it as a 2-dimensional table. And so what we do is we started experimenting with it with like wooden tiles and things like that. And then we made some handmade ones out of plastic. They're 2-inch by 2-inch tiles, and they're colored based on whether they're stable or they have a long half-life and are usable, or if they're a short half-life and are not usable. And we had to limit the size of it. We could only really go up to potassium because of just so many isotopes. So what we did is we started practicing with it, and it was a huge hit with our teachers. So American Nuclear Society started mass-producing them 8 years ago, I'm guessing. And it's become really popular, particularly in our region. We see it. Schools have it. The school districts have it, and things like that. So what we do is we have this large vinyl chart, and they have these 2 by 2-inch tiles, and how the students start out, they each are assigned an element. You know, a student maybe has sulfur or aluminum, and so they put it on a periodic table, and so they know that typically that's a comfortable place for them. And we've seen this actually in middle school, high school, and in college students. They all can do this pretty easily. And so what we do then is we have all these isotopes for each one, and they have to stack them vertically under that initial tile that was the periodic table. And in that, you can start to see some symmetry in the colors from stability. And so the kids have fun, kind of it's hands-on, and then we take that and, like I said, convert it to the chart of nuclides. And when you do that, you lay out this, you can see very plainly, the students see it. They help each other, and they can see this line of stability. This green line is the line we use for stability, and then on either side of it, there's a symmetry as for long-lived half-lives and to short-lived half-lives. Everything is moving towards the line of stability. And all nuclear technologies rely on the phenomena of the line of stability. That's kind of the key of the whole kit. And one of the interesting things about that is we use that kit to describe that almost all science is nuclear science. So you pull out carbon-14, radio dating for archaeology, carbon dating. That is a nuclear science. People aren't afraid of that. There's no myth associated with that. So it's not part of a culture in a negative way. So you can start talking about nuclear science and all these positive ways that it's touching, just like what Mary Lou said earlier. We use fluorine-18 for medicine. We talk about potassium-40 for radio dating stones and rocks in geology. And we talk about how potassium-40 is in our bodies. All living beings have potassium-40 in them. It's part of electrolyte that is needed for life. And so I think a 150-pound person has about 4,300 disintegrations per minute. That's gamma rays coming out of their body for about a 150-pound person. We are natural. We live we're naturally radioactive. We live in a radioactive world, and so it's part of that. The kits, I've seen the best use of them where they'll have a school district will get one, and they'll check them out to schools because schools can use them on a rotating basis in their school district. I've seen it where local universities will have them, and they'll check them out to teachers. I know the University of South Carolina at Aiken has 3 of them, and they check them out to teachers regularly. The Furman University in South Carolina in upstate, probably 2.5 hours from where I am, they have 2 kits. And that middle picture with the students, that's a undergraduate general chemistry class where they're using it. And you can see I think the one young woman is up on the counter to get closer or look to put her isotope in the right place. So they really do get engaged. And so it's been a popular use in our region, and I know it's been all over the nation. Janice, I don't know how many you guys have given or sold a lot of them, and you give them away at teacher workshops as well. So
right.
I'm proud of the work we're doing. I actually was just 2 weeks ago at Plant Vogel with their young engineers, showing them methods of how to do nuclear outreach, and so it's been a pretty useful tool.
And now we're going to talk about measuring radiation. This is discussed and taught in one of our Navigating Nuclear lessons, so it's important for us to pass that information on to students. And part of Navigating Nuclear is there is a professional development video, and Candace Davison, who is the Assistant Director of Education and Outreach, a licensed senior reactor operator at the Radiation Science and Engineering Center of Penn State University, is the ANS member who is featured in that video. So, Candace, why don't you talk about Navigating Nuclear and measuring radiation?
Sure. Hello, everyone. So the video lesson is a good resource to look through and things. But one of the things, and Mary Lou already talked about it, and others, is emphasizing that radiation is everywhere as part of our natural world, and then trying to, in this lesson, learning about how much radiation we receive, and compare and contrast, because there is radiation everywhere. So how much is too much? Is there a dangerous level? And and also emphasizing that it has to be whole body versus like cancer therapy. So then detecting radiation. So as shown, we've used some of the old civil defense, those yellow Geiger counters. If you have other detectors at your facility, that's great. Teachers and students love to use the real detectors. And then looking at in this lesson how radiation can be used to improve our world. So the important thing for this is, as you see on the image there, the teachers are holding the yellow Geiger counters. Now, a lot of these would have been trashed, and there's a story that ANS actually got wind of that and has recovered many from the dump, essentially, to use to give to teachers because they still work. So the first thing is to make sure that the Geiger counter works. So we have the teachers put it together, emphasize don't leave the batteries in there. Also, the fact that if you turn it on and if it's on and the batteries, you're touching the battery area, you may get shocked. So some of the basic, components of safety and handling things with a pretty high charge. Those detectors, they need a headphone if you want to hear the clicking. So, or there's a way to adapt to put a speaker in there, or some people take the headphones. The teachers have used the headphone input and just use their cell phone, right, to help record it or make a kind of an amplifier. So the first thing we do is we kind of how this works, the care and feeding of the Geiger counter. Then understand that there's background radiation. So one of the things we can do is just take a count, and again, I emphasize this, 4 15-second counts. How many clicks do you hear in each 15-second, of that minute? And hopefully they'll see that it's not a constant. So we ask, what do you notice? Try to be more exploratory, as they call it, investigative. So what do you notice about the clicking? Do you notice that the needle moves when it's clicking? It may or may not, depending on the scale. And that's something that we talk about is how to change the scale. But the click rate is not affected by the scale. So they can always use the amount of clicking, detection. So each time it clicks, it's detecting radiation. And that is not affected by what scale you have. So we have them do some observations, emphasize background, and then test things that might be radioactive. And again, depending on how much radiation it's giving off, it may be easy to detect, or they may have to leave the detector there for a little bit longer and really assess, is it radioactive or is it really just background? And that gives us a chance to talk about how environmentally we need longer background counts, or maybe even a complementary background reading machine while you're doing the detection to really see if it's truly radioactive or it's just background. So the other important thing to note is that these counters are not calibrated, these detectors, so you can only semi-qualitatively, so yes, this material reads more than that material, but you can't actually say exactly how much is coming out without the calibration. And again, if you're at a plant or a university where you have calibrated detectors, you can talk about the calibration process, possibly if teachers have questions, and why that's needed. So we do talk about that. And again, it's resources that you have available near you. So if you have some Fiesta ware, maybe some old lantern mantles with the thorium in them, maybe some Vaseline glass, the things that you might find that are naturally radioactive, or they're put in their consumer products that are radioactive, you can go through and use those for the teachers to test. Again, there's kits, there's some websites you can go to find consumer products that are radioactive. Again, some older things like the radium clocks and the dials and things, and just some rocks, carnotite and some natural rocks. Some granites are more radioactive than others. So testing the materials and then noticing. You could even put shielding materials in between and notice, what material stops that radiation, and can get into that discussion on, the shielding aspect, and maybe the type of radiation has an input as to why this material shields or doesn't shield that radiation. So again, depending on where this is in your workshop, you may get into some of the more details about the type of radiation, how it's shielded, and things like that. So that's kind of a quick overview of how we use it. I will say that on the video, they're showing us racing by all the materials that we're supposedly detecting, just to show as an example of things you might detect, but you would not use the Geiger counter that quickly if you're truly trying to detect radioactive material, radiation coming from that material. But it is a pretty good overview for teachers. It's a 3-day, it's meant for a 3-day class session, but it's a good resource to kind of learn some of those concepts.
And now we'll bounce back to Eric Loewen, who will talk to you about our nuclear energy module.
Thank you, Janice. We worked with Discovery Education to produce curriculum for middle schools. And one of the deliverables we had with them was to do a virtual field trip. And that virtual field trip was at Palo Verde Nuclear Power Station in Arizona. And from that effort, we got some great video and a good explanation of how a nuclear power plant works from the perspective of the plant operators. The children in the classroom are able to see the scale and scope of a large nuclear generation facility, and they get to see the sustainability in the context that the city of Phoenix uses their wastewater or is discharged to the plant where they use that for their cooling water, so that there's that synergy of the plant's needs for cooling water. Also, because ANS paid for Discovery Education, it is available to the members or teachers that are part of Discovery Education, and it's available to anybody that has access to the web. And on there, as a provider of a workshop or providing tools to the teacher that you know in your class or that your kids are going to, they would have the ability to get a part of the digital lessons, this virtual field trip, STEM starter guides, and they're all in compliance with the national science standards. So it's a great resource that we are very proud of that we just got done creating.
All right, thank you. And now, Mary Lou, if you could take us quickly through the nuclear fuel cycle module and what the goals are for that one.
So the nuclear fuel cycle is it's not directly addressing that nuclear processes standard, but I think it's an important thing for teachers to understand and just have an overview for. Because the nuclear fuel cycle essentially is the various points along the cycle are the sources of the types of waste that come from nuclear power. And I can't tell you how many times I've had people say, yeah, well, we like nuclear power, but what about the waste? Okay, so waste really isn't the final frontier of nuclear. We know what it is. We know how to work with it and manage it really quite safely. But it's important for us to give that information to the teachers. So we talk about what it is. For example, it's piles of rock outside of a mining facility, not at all a unique thing to nuclear. We talk about the mill tailings, which is what's left after the uranium is leached out of the ore. That material, well, if you've been listening to the news recently, there was a mill tailings dam from a coal mine in Brazil that burst, and that stuff is toxic. So it's less about the fact that it's radioactive and it just has chemicals in it that were used to leach the material out of the ore. There is the depleted uranium that results from the enrichment process that's sitting in canisters and not really having much of a use at this point in our industry. You have the fuel after it comes out of the power plants that Eric mentioned, and this is where the concentration of activity is. So spent nuclear fuel is where, okay, that's where the activity is. And I think it's helpful to show the teachers, okay, this is where the really high level of activity is, but it's also the smallest volume of all the waste. So typically we'll talk a little bit about the classifications of waste and how the lowest level of waste is the highest volume and it goes to this repositories, no problem. And that even when you get to the highest level of waste, it is a ceramic, it's contained, it's very safely managed where it is. And yeah, eventually by policy in this country, we're going to have a repository. And of course, the extent to which you want to talk about all of the politics involved, certainly, up to you. But the teachers are interested a little bit, especially depending on where you are in the U.S. People in the Southwest maybe are more aware of the Yucca Mountain aspect of waste than others might be. Probably one other thing that I think is important is maybe only if teachers bring it up, but typically when I talk about waste, I try to just give them an overview. Okay, this is waste from the commercial nuclear power, but there are other flavors of waste that are on the government side, and you might hear about those. You might hear at the various national labs or military facilities where there has been weapons production over the years. There is some waste that hasn't always been all that well handled, and so there are cleanup projects going on there. If anybody is interested in that, you should at least, I think, have that as a backup, because when you hear that on the news, that, there's a tank leaking in Washington State, I think it's important for teachers to be able to distinguish between that and what's happening in the nuclear power industry, because they're pretty different animals. Just a quick overview then, the topics: facts versus perception of waste, types of waste, where it's stored, and then open versus closed fuel cycle, and how really very safe it is throughout the entire process for the uranium fuel cycle.
Thank you, Mary Lou. Candace is going to take us through another activity that's really more about the actual activity than it is about a lesson. So, Candace, tell us about visualizing nuclear processes.
Okay. I love this activity when we do this at our facility. We're building, cloud chambers, and it's one of the favorite activities because you see the trails, little clouds that basically the ionization trails that have been left behind by the particles, and you can see these paths. So I emphasize that we don't actually see the radiation, but we see the path or the trail. And another analogy would be like a contrail in the sky with a jet. So these particles are invisible, but it helps us see where they've been. And I encourage, again, with the investigative process to, observe the trails. What do they find? What do they observe? Some trails are thicker than others. Some don't go as far. Are they all coming from? Usually, there's a source in there just to facilitate the fact that we want to see some trails. But background radiation, if there's nothing in there, you can see background. So different, characteristics of the trails. So just a few things as far as helping to ensure that you have a successful cloud chamber activity. Make sure you have thick gloves, because if you're dealing with dry ice, and most of these use dry ice, you don't want to get burned. You can get burned from dry ice. In the north, where I live, we don't have dry ice at the grocery stores. So south and western U.S., apparently they do, and it's easy to get. But where I live, we've had teachers drive 50 to 100 miles to get dry ice. So here at Penn State, we have the creamery, and they have dry ice. So that's lucky for me. And we do a lot of demonstrations here because it's so hard for a lot of teachers to get that in their location. You can get it. Some hospitals those be shipping materials to hospitals, and if you have a friend there, they might give you the dry ice that were shipped in those containers. Creameries and some other places, you can look it up. Pellets are a little better just because they're easier, a little more surface area the better, but if you have blocks, you just have to have a chisel and a hammer and break them up. Again, be careful with handling. We use alcohol, either isopropyl or ethanol, and you want to use a higher percentage, 90% or higher. So the isopropyl in the drugstore, if it's 70%, it won't be quite as good as if you have the higher percentage, 90%. So you put the alcohol in, you let it saturate, and then place it on the dry ice to super cool it. And then we found that if you rub your hands together and then put your palm on the top of the chamber to kind of give a super saturate the atmosphere, a top, warm top and a cool bottom helps to bring more of that alcohol into the atmosphere to make it ideal for forming clouds and these trails. And the other suggestion is always have more than one cloud chamber, because sometimes they're finicky. The high humidity areas, it's harder just because of the humidity. So if you have 3 or 4, at least one will work, and everybody can see a good working one. And sometimes some take longer than others to start moving and stuff. So just if it doesn't work at first, give it a few minutes. Rub your hands together, put your hand on top, then move your hand away when you look down and try to see those trails. So those are my kind of suggestions for how to make a successful visualizing radiation process here.
Thank you, Candace. And now I'd like to quickly go over using the modules, because I would like for us to have time to answer your questions. The modules are going to be available to anyone who wants to use them from the ANS website, and the URL for that is on the slide, and the slides will be available for your use. These slides included in the modules are a PowerPoint, instructions for using the module and any activities that are included, sample activity sheets if that's appropriate, and links to lessons that coordinate with the presentation. At the ANS national meetings, we do a full day. That means we use all of the modules, and we do them at the national meetings because our A team, who you've all just heard, is available. There are other options, though. You can do shorter workshops. You can cover fewer subjects, more in detail. You can buy 2 or 3 modules. You can do 1 module if you like. Go to the teachers to teach them. Another idea that has some good research behind it is to spread out the learning with 1 or 2 modules each session so that teachers go back and they work with what they've learned and they can come back to the next session and share. Teachers love to share. We have a number of different ways that we're supporting our workshops. For ANS members, there are printed materials, including teacher guides that you can access through our Public Information Assistance Program, which we effectively donate the materials up to a $500 value. We also distribute Geiger counters and radioactive sources, as well as cloud chambers, to ANS members. Things that are available free to everyone are the Navigating Nuclear website. Not just ANS members, anyone can access navigatingnuclear.com. And there is a workshop guide on the ANS website, and I've included the URL there. It's an extensive guide to putting on a workshop, including promotion and how to work with your site supplier. There are also a number of resources that are available through our website, and you can download those. You can purchase copies of them to distribute, or if you're an ANS member, again, we can supply you with those. We have a very popular radiation dose calculator. We're working on converting our teacher resource guide to a Navigating Nuclear Science companion guide. And this is what the teacher workshop guide looks like on the website. And with that, are there any questions? I did see a question earlier about whether climate change was addressed in our workshops. It's not specifically addressed, but the nuclear energy lesson and workshop module includes having students examine all of the energy options that are available and doing a comparison among them. The benefits of nuclear, obviously, are clean air, and that is emphasized in the lesson that the teachers share with their students.
I was going to comment there. The medical. There's a whole session, right, Janice, on the medical isotopes and medical. The emphasis on radiation and medicine, basically applications in navigating nuclear, and then you can also use that to talk about some other like sterilizing many consumer products and things just that they can't be sterilized by traditional means, using radiation, and that always surprises people when they find out that their contacts or their ophthalmic ointment might have been sterilized by radiation.
We have a question here. Nathan asks, I get a lot of questions that are really targeted towards radiation versus contamination. Do you have a good demo or slides to explain the difference?
Mary Lou?
I think I can address that. So I do in the slide presentation that we're converting now to line up with the radiation basics part of the NGSS. Yes, I address that directly and say, okay, there's a huge difference between a radiation contamination, and there's a slide, but of course I will also, when I demonstrate that, do something, for example, like I will put a cookie on my orange Fiestaware and show that the plate is radioactive, take the cookie off, show that the cookie is not radioactive, and eat it, and say that, okay, the plate is radioactive, the cookie was irradiated, and give a lot of examples like that. And usually I say this to my students as well, if you walk out of this room having nothing else retained in your brain, the difference between irradiation and contamination is key.
And then I've used, just to go along with that, anybody that's baked, with flour, and I have a friend who's got a gluten issue now, so she can't even use flour. So, flour in the kitchen that gets places, that's your contamination. I mean, that's a simple thing. Or mud that people bring in from outside. I mean, simple, types of analogies, evidence.
Okay, we have another question. It says, are there particular lessons geared towards high school versus preschool?
At this point, we don't have any preschool lessons. The lessons on navigating nuclear are specifically targeted at middle schools, but the concepts that we address during the teacher workshops go from middle school concepts and even third grade up to and through high school. So we're addressing topics that all teachers run into when they're talking about atomic structure, for instance, in fifth grade and through middle school, where they're also talking about forms of energy and resources that we use in living on the planet. And then in high school, the focus is more on the chemistry and the physics involved in nuclear processes themselves.
Okay, we have another question. It says, do you discuss the influence of the ionizing radiation on human body?
Yes, there's a slide in the presentation that talks about, it sort of breaks it down, okay, and it says, now remember, this radiation from the nucleus is quote-unquote ionizing radiation. It creates ions, that's what it does. And so it creates ions of the atoms and the cells in your body, and I break it down to what are the possible outcomes there. Well, there could be no change in the cell. There could be a benign change in the cell, or there could be a change that results in what we know as cancer. That I talk about, you could replace the ionizing radiation part of this discussion with a lot of other influences, chemical, for example, and it has the same result, that it may or may not change the cell, and this is the result. So that's one thing I do. But then I also talk about, I look at dose numbers and say, okay, this is an average annual dose, and I don't stress units so much because the units don't really matter. It's a relative thing. So here's the average annual dose. Here's, and that's for your whole body. Here's the dose you get when you take a flight from Idaho to South Africa. Here's the dose you get just to an organ for this treatment. And it gives an idea of what doses are normal. And then I compare that to doses for things like the Hiroshima and Nagasaki bombings, and show that you have to get huge doses before it's even detectable by a doctor, so that basically all the doses we receive on everyday average people are well within the range of normal.
Okay, we have another question. It said, what subjects, physics, chemistry, environmental science, should be teaching these modules? The state standards for each subject changed at my old high school, so it gets juggled between these classes, which are taught by different teachers. So, which subjects?
Can I answer all of them? You can fit them into almost anything, and I think that's the point. Is I don't think it should just be only one subject, because there's so many applications from earth science, space science. I mean, there's so many things. So physics, chemistry, environmental. So if a teacher can include something, all the better. That's my opinion.
All right. Specifically, nuclear processes at the high school level are addressed on the college preparation classes during chemistry. More advanced concepts regarding nuclear processes, like fission equations and things like that, those are addressed in AP classes, and particularly in physics. At the middle school level and the grade school levels, you can run across sources of energy in comparison at the earth science level. Sixth grade, we have the NGSS here in Illinois, and in sixth grade, my daughter did a comparative study of the different types of energy generation, and nuclear was part of that, along with, fossil fuels and wind and solar. Of course, it's kind of hard to build a sample reactor that will generate electricity in your classroom, but that's something that we've addressed in the Navigating Nuclear lesson that is for the middle school and is a comparative study of energy's resources. Also, at the 5th grade level, atomic structure is required in the NGSS. So that's required in the physical science, but in 5th grade, it's all sciences all together. There's no distinction between biology and at least in the student's mind, between biology and chemistry and physical science.
We have some more questions. Is showing, teaching, explaining electromagnetic spectrum effective?
I do it because I think it's important to explain that gamma radiation is the electromagnetic spectrum, and I have a slide, a picture, that looks across the entire spectrum from gamma rays, to visible light, to radio waves. And also, depending on the level of the students, you can talk about the fact that, if you met a gamma ray on the street and it was walking beside an X-ray walking on the street, you wouldn't necessarily know which was which, right? They're both electromagnetic radiation, and they can have exactly the same energy. The difference is that one comes from the nucleus, the gamma ray, one comes from outside the nucleus, the X-ray. Go ahead, Candace.
Just a quick, in the old days, you used to be, X-rays, because of the diagnostic X-ray machines, they had typically lower energies than gamma rays, but now with linear accelerators, like Mary Lou said, they could be the same energy. My demo, I've used a jump rope, making the wave and, a big wave, versus small waves, many waves per second, right? And the people on the other end of the jump rope can feel the difference in energy transferred. So as a visual, we've also, at a recent workshop, a teacher just said, why don't you just use your finger and make a wave, in front of you, and, up and down, make it 1 wavelength in a second, then 2 wavelengths in a second, and then 3 of the same amplitude, right, 10, and they can feel how much more energy just to make those waves in that quick time. So just it is a hard concept. Like why is this ionizing and it's a wave, particle wave, and that is not. So those are some ways to help. And I do feel it's important to emphasize, show this spectrum, and then try to emphasize the energy that wave is carrying.
Right, and the electromagnetic spectrum is something that's included in sciences at I'm trying to remember if it goes down to 5th grade. I believe it does go down to 5th grade. So students need to know that the spectrum goes from, radio waves all the way up to gamma rays and beyond. And they do need to know the difference between radiation that is non-ionizing and ionizing. So those are subjects that are covered in curricula.
We have another question. Any best practices on promoting teacher workshops to best ensure achieving the proper, and they put this in quotations, critical mass of attendance at a workshop?
I think the most important thing to do is make sure that you are planning your workshop for a time when teachers are available. The end of the school year is not a good time, because teachers are going to graduations and planning for their vacation. The 2 weeks after school lets out is a really terrible time, and we've had poor attendance at those. Spring break is a good time. Going to the actual school will guarantee that you have teachers there, and you also need to do promotion. When we promote our workshops, we purchase a mailing list from the National Science Teachers Association. They can do a breakdown of the areas that you're interested in reaching, and usually you go beyond what you think you need to reach because teachers will go a long way to learn nuclear science. They don't get that kind of content in the workshops that they generally are offered through their school. So we send out a postcard to teachers, inviting them to the workshop. That's where our primary number of teachers come from. We can offer a discount to teachers that we get through the National Science Teachers Association. I can't think of the initials, NSTA. There are also state science teacher associations. The lists from them are a little bit less expensive. And all of these science teacher associations are happy to let their membership know about any workshops that are available to them. You can also get online with the environmental educators will post notices of workshops. The National Science Teachers Association has an events page, and they will post. Also send out a press release to each of the teachers associations, the NSTA, and to the state teachers associations. So send that press release or a flyer to the school districts in the area. When we were in Las Vegas, there is a huge school district. It covers pretty much the entire city. And their curriculum director took our flyer and distributed it to every school in their district. So those are the kinds of things that you can do to reach as many teachers as possible.
Okay, we have another question. Thank you, Janice. Once we explain measuring radiation, what's the answer you give to how much radiation does it take to hurt me? Going into LNT isn't probably the best answer, but is there a slide showing X dose equals Y health effect?
Oh boy, that's a touchy one. So again, depending on the level of the student, I mean, it depends on how far the teacher wants to go. But the teacher themselves, I think it's certainly appropriate to say, okay, here is the linear no threshold theory. Here's what it says, that, we have all these data at the really high doses, and we know that those really high doses, there are effects. And the other thing you can say there is we don't have data really that tells us what happens, or at least we haven't done a lot of analysis of data at the lower doses. But what we do know is that up until this certain dose, and there are slides in the radiation basics presentation that give you numbers, up until certain doses, there's no observable effect. And we're talking like 250,000 millirem or something like that. So you can say that the regulations are based on this theory, but it is not consistent with what we really know about doses. So the 250,000 is a number that is when maybe the doctor can first see a small change in your blood chemistry, but that doesn't mean it's dangerous, okay? So it's a touchy thing, right? But I think you can show relative magnitude of doses that actually we know cause a problem versus what people are exposed to on a regular basis.
Right. We approach it from a comparative point of view. I mean, a student understands that they get x-rays on their teeth and that they're pretty much fine. But telling a student how much radiation will hurt them I don't think it's possible to do that without knowing particular circumstances, because it's going to depend very much. I know that's not a satisfying answer, but it really does depend on a number of factors.
Okay. We have time for probably one more question. So somebody asked, how do you persuade school administrators to adopt nuclear science into their school's curriculum if it is not required by existing standards?
The current standard from the National Science Teachers Association well, they help develop it, but it's not necessarily their standard. The next generation science standards have been adopted by 19 states and by the District of Columbia. They include nuclear processes as part of what should be assessed. Now, that said, there are 21 additional states who have adopted standards that are based on the same framework that the next generation science standards are. The primary reason for not adopting the NGSS straight out of the box is because states want to be able to teach that climate change is not a settled science, or they want to also be able to teach intelligent design. In every case I've looked at, the nuclear processes standard remains intact. So I guess the answer to that is that nuclear processes are required in most states. If you have a particular state in mind, it would depend very much on why nuclear processes is not included, but you'd also have to review the actual standard and make sure that nuclear is not covered in that standard in some way, because it may not be in the same place that it is in the NGSS or in standards that are based on what's called the National Framework for Science Education.
All right. Well, at this time, I think we're going to end this presentation unless you have anything further to add, Janice, or any of the panelists?
No, just thank you very much for attending, and please don't hesitate to contact me. My email address is on the screen, but if you cannot see the screen, it is JLindegard@ans.org.
Okay. Thank you all for attending Navigating Nuclear Science, Creating Teacher Workshops. Have a great day.